Before you can design a successful transportation project, one mistake in the planning stage can lead to higher costs, safety problems, delays, and major design changes later. And this is exactly why project planning and alternatives analysis are so important on the P-Civil Transportation exam. In this first section, you will learn how transportation engineers predict future traffic, compare different project alternatives, evaluate environmental impacts, and make the decisions that shape an entire transportation project before construction even begins. These may seem like basic concepts, but they can become easy points on exam day when you understand how they work together. So stay with me through this complete video, because we will cover all 6 sections of the P-Civil Transportation Practice Test. I have also included a free study guide with some of the most important questions in the description, so make sure you check it out. And watch the complete video, because at the end, I will share a simple strategy that can help you prepare more effectively and pass your P-Civil Transportation exam with confidence. Now, let's begin with Section 1, Project Planning and Alternatives Analysis. Let us start by looking at the big picture of transportation planning. Before we can design a new highway or expand an existing road, we have to understand the specific problem we are trying to solve. This might be severe traffic congestion, a high rate of accidents, or the need to connect a growing residential area to a busy city center. Identifying this core problem is known as defining the purpose and need of a project. The purpose and need statement is a formal document that guides every single engineering decision moving forward. Once we know the specific problem, we have to predict what the traffic will look like in the future. This process is called traffic forecasting, and it is a major part of the planning phase. Engineers do not just look at how many cars are on the road today. They look ahead 20 or 30 years to estimate future demand based on population growth, economic trends, and new land development. If we only design for today's traffic, our brand new road will be jammed with cars the very day it opens. To predict this future traffic accurately, planners often use a 4-step travel demand model. The very first step of this standard model is called trip generation. Trip generation answers a simple question, which is, how many total trips will start or end in a specific area? For example, a massive shopping mall will generate thousands of trips every day, while a small neighborhood will generate far fewer. We use specialized data, often from the Institute of Transportation Engineers, to estimate these daily numbers. After we figure out how many trips are being generated, we move directly to the second step, known as trip distribution. Trip distribution figures out where all these individual trips are actually going. It matches the starting points, like residential homes, with the ending points, like corporate offices or local schools. Imagine a visual map with lines connecting different zones of a city. The thicker the line on the map, the more people are traveling between those two specific areas. The third step in our traffic forecasting model is mode choice. Mode choice determines exactly how people will travel between their starting and ending points. Will they drive their own personal cars, take a public transit bus, ride a bicycle, or simply walk? This decision depends heavily on what travel options are currently available, how much they cost, and how long the commute takes. Understanding mode choice helps engineers decide if a project needs new car lanes, a dedicated bus route, or extensive pedestrian sidewalks. The final step of the 4-step model is route assignment. Now that we know where people are going and exactly how they are getting there, route assignment predicts the specific physical roads they will take. Think about how you use a GPS navigation app on your smartphone. You usually choose the fastest or most direct route available to your destination. Route assignment software does this exact same mathematical calculation for thousands of vehicles at once, showing us which highways will be the most crowded. Armed with our detailed future traffic predictions, we can start brainstorming different ways to solve our initial transportation problem. This brings us to alternatives analysis. We rarely have just one single option when designing a civil engineering project. We might seriously consider widening an existing road, building a completely new bypass highway, or perhaps improving public transit instead. Each of these potential solutions is called an alternative. One of the alternatives we must absolutely always consider is called the no-build alternative. The no-build alternative simply means doing nothing at all and leaving the existing road exactly as it is today. We use this as a baseline to compare against all our other expensive engineering ideas. If building a new highway costs $50 million, but only saves drivers 2 minutes of travel time compared to doing nothing, the no-build alternative might actually be the smartest choice. When evaluating these different design alternatives, engineers rely heavily on economic analysis. We need to make sure that the financial benefits of a project outweigh the heavy construction costs. One very common method you will see on the certification exam is the benefit-cost ratio. To calculate this, we divide the total financial benefits, like saved time and fewer accidents, by the total costs of construction and maintenance. A ratio greater than 1 indicates that the project is a solid investment for the public. Another highly important economic tool is life cycle cost analysis. A new highway is not just paid for once during the initial construction phase. It requires ongoing maintenance, regular repaving, and eventual replacement over many decades. Life cycle cost analysis looks at the absolute total cost of owning and operating that highway over its entire expected lifespan. This critical analysis helps planners choose materials and designs that might cost more upfront but save millions of dollars in future repairs. As we narrow down our specific design alternatives, we must strictly follow federal environmental laws. In the United States, the most important of these laws is the National Environmental Policy Act, which is commonly referred to as NEPA. NEPA requires government agencies to thoroughly evaluate how a proposed transportation project will affect the natural and human environment. You cannot simply bulldoze through a forest or a neighborhood without a highly detailed environmental review process. Depending on the physical size of the project and its potential impacts, NEPA requires different levels of formal documentation. If a project is very small, like repainting traffic lines on a road, it usually qualifies for a categorical exclusion. This means it has almost zero environmental impact and can proceed very quickly without heavy paperwork. Knowing exactly when a categorical exclusion applies is a very common question on the professional engineering exam. If a project has some potential environmental impacts, but we are not entirely sure how severe they are, we must prepare an environmental assessment. This is a concise public document that provides just enough evidence to determine if the impacts will be truly significant. If the assessment shows that the project will not cause major environmental harm, the agency issues a finding of no significant impact, which officially allows the project to move forward to the final design phase. However, if the project is massive, like building a brand new interstate highway, it will likely require an environmental impact statement. This is the most incredibly detailed and rigorous level of environmental review under NEPA. It requires extensive scientific studies on air quality, noise pollution, wildlife habitats, and clean water resources. The environmental impact statement process can take many years to complete and involves significant input from the local community. Let us talk about a specific environmental concern that transportation engineers face frequently, which is noise pollution. Highways are incredibly loud, and building them near residential areas can severely impact the daily quality of life for those communities. During the planning phase, we use specialized computer software to predict exactly how loud the traffic will be at nearby homes. If the calculated noise levels exceed certain federal thresholds, we must incorporate noise mitigation strategies into our design. The most common and effective way to reduce highway noise is by building noise barriers or sound walls. These are the tall concrete or wooden walls you often see lining the edges of urban freeways. They work by absorbing sound waves or physically forcing them to travel over the top of the wall, creating a much quieter shadow zone for the houses located directly behind them. Placing and sizing these walls correctly is a highly practical skill tested on the P exam. Another critical environmental factor is managing dangerous stormwater runoff. When we pave over natural dirt and grass with solid asphalt, rainwater can no longer soak gently into the ground. Instead, it rushes rapidly off the road surface, picking up harmful oil, heavy metals, and debris. Planners must design retention ponds and complex drainage systems to capture and clean this polluted water before it flows into local rivers and sensitive streams. Finally, we must also carefully consider the social impacts of our transportation projects. We cannot design a massive highway that completely cuts off a local neighborhood from its schools, parks, or grocery stores. This requires careful consideration of safe pedestrian access, dedicated bicycle lanes, and overall community cohesion. A truly successful transportation project connects people together and improves their daily lives without destroying the physical communities they live in. Congratulations on successfully completing the very first section of this course. You now have an incredibly solid understanding of project planning, traffic forecasting, and the environmental reviews that shape our modern roadways. I highly encourage you to complete the attached practice test right now, because answering practice questions is the absolute best way to improve your retention and get truly ready for the exam. The practice test is included right here with this lesson to help you actively reinforce everything we just discussed. Keep up this great active learning, and I will see you in the next section where we will dive into traffic engineering and capacity analysis. Welcome to the second section of our course. In this lesson, we are going to explore traffic engineering and capacity analysis, which is the absolute heartbeat of transportation engineering. You will learn how to measure traffic flow, analyze intersections, and determine exactly how many vehicles a roadway can handle before it breaks down into gridlock. Understanding these mechanics is incredibly important because it allows us to design efficient systems that keep people moving smoothly and safely. Get ready to master the fundamental principles of traffic movement, because this knowledge will give you incredible confidence as you prepare for the exam. Let us start by looking at the three fundamental variables of traffic flow, which are volume, speed, and density. Volume is simply the number of vehicles passing a specific point during a given time period, usually measured in vehicles per hour. Speed is how fast those vehicles are traveling down the road. Density is the physical number of vehicles crowded into a specific length of roadway, usually measured in vehicles per mile. These three core variables are completely interconnected, and changing one will always mathematically affect the other two. When we analyze these traffic variables, we must divide transportation facilities into two distinct categories. The first category is uninterrupted flow facilities, like major interstate freeways, where there are no stop signs or traffic signals to hold movement. The second category is interrupted flow facilities, like downtown city streets, where traffic signals and pedestrian crosswalks force vehicles to stop frequently. The mathematical models and engineering manuals we use for these two categories are entirely different, so you must always identify the facility type first on your exam. To design a roadway properly, we do not use the traffic volume from a quiet Sunday morning or the absolute highest volume from a massive holiday evacuation. Instead, engineers use the design hourly volume, commonly known as the DHV. The DHV represents the 30th highest hourly volume of traffic expected throughout the entire year. By designing for this specific hour, we ensure the road operates smoothly for almost the entire year without overspending public money on extra lanes that sit empty most of the time. Traffic does not arrive evenly over a full 60 minutes, which is why we must calculate the peak hour factor. The peak hour factor is a mathematical value that shows how traffic volume fluctuates within the absolute busiest hour of the day. We calculate it by dividing the total hourly volume by 4 times the busiest 15-minute volume within that same hour. A peak hour factor closer to 1 indicates steady, even traffic flow, while a lower number indicates a sudden, massive spike of vehicles. Once we understand our traffic volumes, we evaluate the roadway using a grading system called level of service. Level of service uses letter grades from A to F to describe how well a road is performing from the direct perspective of the driver. Level of service A represents completely free-flowing traffic with zero delays and high speeds. On the completely opposite end, level of service F represents a total breakdown of traffic flow, with long delays, creeping speeds, and terrible frustration for the everyday driver. This brings us to the core concept of roadway capacity. Capacity is defined as the maximum hourly rate at which vehicles can reasonably be expected to pass a point during specific roadway and traffic conditions. Think of a highway lane like a water pipe. There is a maximum limit to how much water can push through that pipe before it backs up, and there is a maximum limit to how many cars can fit in a lane before traffic jams occur. For a standard freeway, the base capacity is typically around 2,400 passenger cars per hour per lane. However, that base capacity assumes every single vehicle on the road is a standard passenger car, which is never true in the real world. We must account for the presence of large semi-trucks, recreational vehicles, and heavy buses. These massive vehicles take up much more physical space and accelerate far slower than normal cars, especially when driving up steep hills. Engineers use a mathematical adjustment called a passenger car equivalent to convert these slow, heavy trucks into a standard car value for our capacity formulas. Another critical metric for freeway analysis is the free flow speed. The free flow speed is the average speed that passenger cars travel when traffic density is so incredibly low that drivers are not influenced by other vehicles around them. It is essentially the speed you would comfortably drive on a completely empty highway late at night. We use the free flow speed as our baseline starting point to calculate how much traffic will slow down as the highway becomes more crowded during the morning commute. When you are tested on freeway analysis, you will focus heavily on basic freeway segments. A basic freeway segment is a straight stretch of highway that is completely unaffected by merging traffic from on-ramps or exiting traffic from off-ramps. To find the level of service for these basic segments, we strictly use traffic density as our primary performance measure. If the density stays below 11 passenger cars per mile per lane, the roadway earns a perfect level of service A. Not all freeway sections are basic segments, so we must also analyze complex weaving segments. Weaving segments occur when an on-ramp is located very closely before an off-ramp. In a weaving segment, vehicles entering the highway must violently cross paths with vehicles trying to exit the highway. This intense crisscrossing movement creates massive friction and slows everyone down significantly. The capacity of a weaving segment is always much lower than a basic segment because of this chaotic lane-changing behavior. Now let us move from uninterrupted freeways to interrupted city streets, specifically focusing on signalized intersections. A traffic signal completely dictates road capacity because a green light only allows traffic to move for a fraction of the total hour. The most important metric for evaluating a signalized intersection is control delay. Control delay measures the average time, in seconds, that a driver loses while slowing down, waiting at the red light, and finally accelerating back to normal speed. To calculate this delay accurately, you must understand the cycle length of a traffic signal. The cycle length is the total time it takes for a traffic signal to complete one full sequence of all its colored lights, from green to yellow to red and back to green again. If the cycle length is too short, not enough cars can get through the intersection during the green phase. If the cycle length is too long, drivers waiting on the cross street will become extremely frustrated and might run the red light dangerously. When the light finally turns green, the vehicles lined up at the intersection do not all cross at the exact same instant. They accelerate one by one, eventually reaching a maximum steady pace called the saturation flow rate. The saturation flow rate represents the theoretical number of vehicles that could pass through the intersection if the light stayed perfectly green for an entire hour. We must calculate this rate carefully to design signal timings that clear traffic jams efficiently and safely. We must also analyze unsignalized intersections, primarily those controlled by standard two-way stop signs. At these locations, drivers on the minor street must wait patiently for a safe gap in the major street traffic before they can turn or cross. The capacity of the stop sign approach depends entirely on how many acceptable gaps appear in the main traffic stream. If the main street is completely packed with fast-moving cars, the minor street capacity drops practically to zero. When traffic demand exceeds the capacity of an intersection, a line of waiting vehicles will immediately begin to form. Studying how these lines grow and shrink is called queuing theory. Queuing theory uses mathematical models to predict exactly how long a line of cars will become and how long an individual driver will have to wait in that line. This is incredibly important for designing turn lanes that are physically long enough to hold all the waiting cars without blocking the main travel lanes. To gather the real-world data needed for all these calculations, engineers conduct various traffic studies out in the field. A spot speed study is used to measure the speeds of vehicles passing a specific single location on a roadway. We use radar guns or pneumatic road tubes to record these speeds, and then we calculate the 85th percentile speed. The 85th percentile speed is the speed at or below which 85% of all drivers are traveling, and it is the primary factor used to legally set speed limits. Another vital field study is the traffic volume study, which simply counts the physical number of vehicles passing a point. In the old days, engineers used manual clickers on a clipboard, but today we rely on video cameras, road tubes, and sophisticated radar sensors. This data tells us when the morning and evening rush hours actually occur in a specific town. Accurate volume data is the absolute foundation of every single capacity analysis problem you will solve on the certification exam. It is incredibly vital to remember that increasing capacity should never come at the expense of human safety. Sometimes, Widening a road to handle more cars can accidentally encourage higher speeds and create more severe crashes. Traffic engineering is a delicate balancing act between moving vehicles efficiently and protecting the lives of drivers and pedestrians. Always keep this balance in mind, because exam questions often test your ability to recognize when a capacity improvement might create a dangerous roadside hazard. Congratulations on successfully completing the second section of this comprehensive course. You now have a fantastic grasp of traffic flow, capacity analysis, and the critical concepts used to evaluate intersections and freeways. I highly encourage you to complete the attached practice test right now, because answering practice questions is the absolute best way to improve your attention and get truly ready for the exam. The practice test is included right here with this lesson to help you actively reinforce everything we just discussed. Keep up this great active learning, and I will see you in the next section where we will explore horizontal and vertical geometric design. Welcome to the third section of our comprehensive course. In this lesson, we are going to explore horizontal and vertical geometric design, which is the actual physical shaping of our roadways in 3 dimensions. You will learn how engineers calculate sweeping curves, manage steep hills, and ensure drivers can see far enough ahead to stop safely in an emergency. Understanding geometric design is incredibly important because it directly controls how fast and how safely vehicles can navigate through a physical landscape. Get ready to master these design principles, because this is historically one of the most heavily tested subjects on the entire professional engineering exam. When we talk about roadway design in the United States, everything revolves around one massive foundational manual. This document is published by the American Association of State Highway and Transportation Officials, and it is universally known as the AASHTO Green Book. The Green Book provides the absolute standard guidelines for designing everything from local residential streets to massive interstate freeways. Knowing how to navigate this specific book quickly and find the correct tables is a mandatory skill for passing your certification exam. The first major concept we will tackle is horizontal alignment, which is how a road curves left and right when you look at it from high above in the sky. When a road needs to change direction, we do not just create a sharp-angled corner that would force cars to slow down to a crawl. Instead, we connect the 2 straight sections of road, which are called tangents, with a smooth circular curve. Designing this circular curve properly ensures that vehicles can maintain their speed without suddenly flying off the road. The most important defining feature of a horizontal curve is its radius. The radius tells us exactly how tight or how broad the curve actually is. A very large radius creates a gentle, sweeping curve that is safe for high freeway speeds. On the other hand, a small radius creates a very tight, sharp curve that requires drivers to slow down significantly. On the exam, you will often have to calculate the exact radius needed to safely accommodate a specific highway speed limit. When you drive around a sharp corner quickly, you can physically feel your body being pushed toward the outside of the car. This outward push is called centrifugal force, and it is actively trying to slide your vehicle off the road. To counteract this dangerous force, engineers tilt the entire roadway surface slightly inward toward the center of the curve. This inward banking of the road is called superelevation, and it uses gravity to help pull the car safely around the corner. However, superelevation cannot do all the work by itself. The tires of the vehicle must also grip the pavement to prevent sliding, which introduces the concept of side friction. Side friction is the physical grip between the rubber tires and the asphalt surface. When we design a horizontal curve, we calculate a careful mathematical balance between the vehicle speed, the superelevation banking, and the available side friction to guarantee the car stays safely in its lane. In some situations, moving instantly from a completely straight road into a banked circular curve can be visually jarring and physically uncomfortable for the driver. To solve this problem, engineers sometimes use transition curves, which are commonly called spiral curves. A spiral curve gradually introduces the turning radius and the superelevation banking over a set distance. This allows the driver to slowly and naturally turn the steering wheel, creating an incredibly smooth and comfortable driving experience. Another critical factor in horizontal design is making sure drivers can actually see around the corner. If there is a tall mountain, a dense forest, or a large building on the inside of the curve, it might completely block the view of an upcoming hazard. We calculate a specific measurement called the horizontal sightline offset to ensure there is enough empty space across the inside of the curve. If a physical object is located too close to the road, we must either remove the object or make the curve larger to restore visibility. Now we must shift our perspective and look at the road from the side, which brings us to vertical alignment. The earth is rarely perfectly flat, so roads must constantly go up hills and down into valleys. We connect an uphill slope to a downhill slope using a smooth parabolic transition called a vertical curve. There are two primary types of vertical curves you must know, which are crest vertical curves that go over a hill, and sag vertical curves that dip into a valley. Before we can design a vertical curve, we have to define the slopes of the straight roads connecting to it. These slopes are called grades, and they are expressed as percentages. An uphill road has a positive grade, while a downhill road has a negative grade. For example, a positive 4% grade means the road rises exactly 4 vertical feet for every 100 horizontal feet you drive. Understanding how to calculate and apply these grades is the starting point for every vertical curve problem. Let us look closely at crest vertical curves first. When you drive up over the top of a steep hill, the road surface physically blocks your view of what is on the other side. If the curve is too sharp, you might not see a stopped car or a fallen tree in time to hit your brakes. Therefore, the absolute primary design control for a crest vertical curve is providing adequate sight distance over the top of the hill. This brings us to a massively important exam topic known as stopping sight distance. Stopping sight distance is the total physical distance a vehicle travels from the exact moment a driver spots a hazard until the vehicle comes to a complete and total stop. This total distance is mathematically broken down into two distinct parts. The first part is the distance traveled while the driver is mentally reacting, and the second part is the distance traveled while the brakes are mechanically slowing the car down. The first part, the reaction distance, depends heavily on human psychology. It takes time for a human brain to see an object, recognize it as dangerous, decide to hit the brakes, and physically move the foot to the pedal. The AASHTO Green Book standardizes this entire perception and reaction time at exactly 2.5 seconds. During those 2.5 seconds, a car traveling at highway speeds will cover an incredibly large amount of ground before the brakes are even touched. The second part is the actual braking distance, which relies on pure physics. The braking distance depends on the speed of the vehicle, the friction of the pavement, and the grade of the road. It takes significantly longer to brake when you are traveling downhill because gravity is actively pushing the car forward. You must know how to calculate this braking distance accurately, because it dictates exactly how long your vertical and horizontal curves must be to keep people safe. Now let us transition to sag vertical curves, where the road dips down into a valley and goes back up. During the bright daytime, you can see perfectly clearly across a sag curve. However, at night, your visibility is strictly limited to where your headlights are shining. Because the road curves upward ahead of you, your headlights will point directly into the pavement instead of shining far down the road. Therefore, the primary design control for a sag curve is providing adequate headlight sight distance. To calculate and compare these vertical curves quickly, engineers use a very helpful mathematical metric called the k-value. The k-value represents the horizontal distance required to change the road grade by exactly 1%. It is essentially a measure of how sharp or how gentle the vertical curve is. A higher k-value means a longer, gentler curve, while a lower k-value means a shorter, sharper curve. You will use k-values constantly on the exam to quickly size curves for different speed limits. Beyond simple stopping sight distance, we must also consider passing sight distance on rural two-lane highways. When a slow-moving tractor is holding up traffic, drivers need a safe opportunity to pass by briefly crossing into the oncoming traffic lane. Passing sight distance calculates the massive amount of clear visibility needed to pull out, accelerate past the slow vehicle, and safely return to the correct lane before hitting an oncoming car. Sight distance is equally critical when designing local intersections. When a driver stops at a stop sign, they need a completely clear line of sight in both directions down the main road to know when it is safe to turn. This clear area is called an intersection sight triangle. Engineers must ensure that no tall fences, large bushes, or heavy signs are ever placed inside this triangle, because blocking this specific view leads to devastating side impact collisions. Finally, we must look at the cross-section of the roadway, which is what the road looks like if you sliced it perfectly in half. A typical cross-section includes the travel lanes, the paved shoulders, and the side slopes. The most critical element here is the normal cross slope, which tilts the center of the road slightly higher than the edges. This slight tilt allows heavy rainwater to quickly drain off the pavement, preventing dangerous puddles that can cause vehicles to hydroplane out of control. Congratulations on successfully completing the third section of this course. You now have a fantastic understanding of horizontal alignments, vertical curves, and the critical sight distances that keep drivers safe. I highly encourage you to complete the attached practice test right now, because answering practice questions is the absolute best way to improve your attention and get truly ready for the exam. The practice test is included right here with this lesson to help you actively reinforce everything we just discussed. Keep up this great active learning, and I will see you in the next section where we will explore transportation safety and traffic control. Welcome to the fourth section of our course. In this lesson, we are going to explore transportation safety and traffic control. You will learn how engineers analyze crash data, design safe roadsides, and use signs and pavement markings to guide drivers effectively. Understanding these safety principles is incredibly important because our ultimate goal as civil engineers is to protect human life on the roadways. Get ready to learn some truly life-saving concepts, because mastering this material will make you a better engineer and help you ace the certification exam. Let us start by looking at how we actually measure and predict safety on our roadways. Engineers rely heavily on a massive technical guide called the Highway Safety Manual. The Highway Safety Manual provides a highly scientific, data-driven approach to predicting how many crashes will happen on a specific road. Before this manual existed, engineers mostly just guessed or reacted to crashes after they happened, but today we can proactively design safer roads before a single car ever drives on them. To predict future safety, we first have to study the past by looking at historical crash data. When a collision occurs, police officers fill out a detailed crash report noting the weather, the time of day, and the exact type of crash. Engineers collect thousands of these reports to look for hidden patterns at specific intersections or highway curves. If we notice that 10 cars all ran off the road at the exact same corner during the rain, we immediately know there is a physical engineering problem we need to fix. Looking at the raw number of crashes is helpful, but it does not tell the whole story. A busy highway will naturally have more crashes than a quiet country road simply because there are more cars. To make a fair comparison, engineers calculate crash rates, which measure the number of crashes relative to the actual traffic volume. Calculating crash rates per million vehicles entering an intersection is a very common task you will see on the professional engineering exam. Once we identify a dangerous location, we need to choose the best way to fix it. This is where crash modification factors come in. A crash modification factor is a special mathematical multiplier used to estimate how much a specific design change will reduce future crashes. For example, installing bright new streetlights might have a crash modification factor of 0.8. This means the new lights are expected to reduce nighttime crashes by exactly 20%. One of the most effective ways to prevent fatal crashes is by designing a safe roadside environment. When a driver falls asleep or swerves to avoid a deer, their vehicle will violently leave the paved roadway. To protect them, engineers create a concept called the clear zone. The clear zone is a flat, unobstructed area of land right next to the road where a driver can safely regain control of their vehicle without hitting a dangerous obstacle. If we cannot provide a wide enough clear zone because of a steep cliff or a solid bridge pier, we must install a physical barrier. Guardrails and concrete median barriers are designed to catch and redirect a drifting vehicle safely along the road. However, barriers are actually dangerous obstacles themselves, so we only install them if hitting the barrier is mathematically proven to be safer than hitting the object hidden behind it. Sometimes we absolutely must place an object inside the clear zone, like a large highway exit sign or a tall streetlight. In these unavoidable cases, we use a brilliant engineering design called breakaway supports. These metal poles are specially designed with weakened joints at the bottom so they instantly snap and fold over if a car hits them. This prevents the heavy pole from crushing the vehicle and saves countless lives every single year. Now let us talk about how we actively communicate with drivers using traffic control devices. The absolute Bible for this topic is the Manual on Uniform Traffic Control Devices, which is commonly called the MUTCD. The MUTCD dictates the exact size, shape, color, and placement of every single road sign, traffic signal, and painted line in the country. This uniformity ensures that a stop sign in California looks exactly the same as a stop sign in New York. The MUTCD divides all traffic signs into three major functional categories. The first category is regulatory signs, which tell drivers about strict traffic laws. Regulatory signs are usually rectangular and feature black text on a bright white background, with the red stop sign being the most famous exception. Disobeying a regulatory sign is a direct traffic violation that will instantly earn you a ticket from a police officer. The second major category is warning signs, which alert drivers to unexpected conditions ahead. These signs are typically diamond-shaped and feature bold black graphics on a highly visible yellow background. Warning signs tell you about upcoming sharp curves, hidden intersections, or pedestrian crosswalks that might require you to slow down. During construction, these warning signs switch to a bright orange background to indicate temporary hazards and active work zones. The third category is guide signs, which provide directional information and distance markers to help drivers navigate. These are the massive green signs you see hanging over interstate highways, showing you which lane leads to your specific destination. Guide signs can also be blue to indicate nearby motorist services like gas stations and hospitals, or brown to point out recreational areas like national parks and historical sites. Beyond signs, we communicate with drivers using long painted lines called pavement markings. Pavement markings are incredibly important because they physically divide the road into safe travel lanes. The color of the paint has a very specific legal meaning. Yellow lines always separate traffic moving in completely opposite directions, while white lines always separate traffic moving in the exact same direction. The pattern of the painted line is just as important as the color. A dashed or broken line indicates that a driver is legally allowed to cross over it to change lanes or pass a slower vehicle. A solid line strongly discourages crossing, and a double solid line means that crossing is strictly prohibited by law. Knowing these simple paint rules is absolutely essential for answering traffic control questions on the exam. When traffic volume gets too heavy for simple signs and paint, we must install a motorized traffic signal. Warrants are the strict mathematical rules found in the MUTCD that tell us when a signal is truly justified. We do not just install a signal because a local citizen complained about traffic. We must prove through detailed traffic volume studies and crash history analysis that a signal will actually improve the intersection without causing massive new delays. Once a signal is installed, engineers must design its specific phases. A phase is the part of the signal cycle allocated to a specific movement of traffic. For example, the main street green light is one phase, and the protected left turn arrow is a separate phase. Designing these phases carefully ensures that vehicles traveling in conflicting directions do not crash into each other in the middle of the intersection. Safety is not just for cars, because we must also actively protect vulnerable pedestrians. Pedestrians have zero physical protection in a crash, so designing safe walking facilities is a top priority. Engineers design raised sidewalks, brightly painted crosswalks, and pedestrian refuge islands in the middle of wide streets. We also program specific pedestrian walking phases into our traffic signals, giving people enough dedicated time to cross safely before the cars start moving again. When designing pedestrian facilities, we must strictly follow the Americans with Disabilities Act, or the ADA. The ADA ensures that transportation networks are fully accessible to everyone, including people using wheelchairs or those with visual impairments. We install gently sloped curb ramps at every intersection corner and place tactile warning panels with small bumps to let visually impaired pedestrians know exactly where the safe sidewalk ends and the dangerous street begins. Finally, we must briefly discuss the incredibly dangerous environment of a temporary construction work zone. When we rebuild a road while traffic is still driving right next to the workers, the risk of a fatal crash skyrockets. We use advanced warning signs, flashing arrow boards, and heavy concrete barriers to separate the workers from the fast-moving cars. Designing these temporary traffic control plans is a massive responsibility and a frequent topic on the certification exam. Congratulations on successfully completing the 4th section of this course. You now have a fantastic understanding of crash analysis, the highway safety manual, and the traffic control devices that guide our daily commutes. I highly encourage you to complete the attached practice test right now, because answering practice questions is the absolute best way to improve your attention and get truly ready for the exam. The practice test is included right here with this lesson to help you actively reinforce everything we just discussed. Keep up this great active learning, and I will see you in the next section where we will explore pavement design and geotechnical engineering. Welcome to the 5th section of our course. In this lesson, we are going to explore pavement design and geotechnical engineering, which is all about what supports our roads from the ground up. You will learn about soil properties, flexible and rigid pavements, and structural layers that allow roads to hold heavy traffic loads for decades. Understanding these material and structural principles is incredibly important because a road is only as good as the foundation beneath it. Get ready to dive in, because mastering these concepts will bring you one big step closer to passing your P-Civil exam. Let us start by looking at the foundation of every single roadway, which is the natural earth or subgrade soil. Geotechnical engineering in transportation focuses on how the ground under the road responds when heavy vehicles drive over it. If the soil underneath is weak or unstable, even the thickest asphalt or concrete surface will crack and collapse very quickly. Therefore, evaluating and improving the subgrade is always the absolute first step in pavement design. To evaluate soil, engineers use specific classification systems, and the most common one in transportation is the AASHTO soil classification system. This system categorizes soils from A1 to A7 based on their suitability for road construction. A1 and A2 soils are coarse gravels and sands that provide excellent structural support. On the other hand, A6 and A7 soils are fine clays and silts that retain water and make terrible foundation materials. To classify soil accurately, we perform a laboratory test called a sieve analysis to determine grain size distribution. We also test fine soils using Atterberg limits, which measure how soil behaves when mixed with water. The liquid limit is the moisture content where soil changes from a plastic state to a liquid state, and the plastic limit is where it becomes brittle. Subtracting the plastic limit from the liquid limit gives us the plasticity index, which indicates how much the soil swells and shrinks. Once we know what kind of soil we have, we must compact it tightly before building the road. Compaction increases soil density, decreases permeability, and reduces future settling under traffic loads. In the lab, engineers perform a Proctor compaction test to create a moisture density curve. This curve reveals the optimum moisture content needed to achieve the maximum dry density out in the field using heavy rollers. We also measure soil strength directly using the California Bearing Ratio test, commonly known as the CBR test. The CBR test pushes a small metal piston into a compacted soil sample and compares the required force against a standard crushed stone sample. Another vital strength metric used in modern pavement design is the resilient modulus, which measures the elastic stiffness of the soil under repeated, rapid traffic loads. Now that we understand the soil foundation, let us look at the two primary types of road surfaces, which are flexible pavements and rigid pavements. Flexible pavements are built with asphalt layers, while rigid pavements are built with Portland cement concrete slabs. The fundamental difference between them is how they distribute vehicle wheel loads down to the subgrade soil below. Flexible asphalt pavements distribute heavy wheel loads through a layered pyramid effect, spreading the weight outward as it travels deeper down. A typical flexible pavement cross-section consists of a thin hot mix asphalt surface course, an aggregate base course, an optional subbase course, and the subgrade soil at the bottom. Each layer going down uses slightly weaker and less expensive materials because the load stress diminishes with depth. To design a flexible pavement, engineers often use the classic AASHTO empirical design method to determine a required structural number. The structural number represents the total structural strength needed to protect the subgrade from traffic damage over time. We calculate this number by multiplying the thickness of each individual layer by a structural layer coefficient and a drainage coefficient, then adding them together. But how do we account for all the different vehicles driving over the road, from light passenger cars to massive 18-wheeler trucks? We use a universal conversion metric called equivalent single-axle loads, commonly known as ESALs. One ESAL equals the damage caused by a single 18,000-pound dual tire axle load. Converting all mixed traffic into cumulative design ESALs lets us design the pavement for its exact expected lifetime damage. Now let us shift our focus to rigid concrete pavements, which behave very differently than flexible pavements. Rigid pavements act like a stiff, solid bridge slab, bridging over small soft spots in the subgrade and spreading the heavy load over a massive area. The three main types of rigid pavements are jointed plain concrete, jointed reinforced concrete, and continuously reinforced concrete pavements. Designing a rigid concrete pavement involves selecting the proper slab thickness based on concrete flexural strength, traffic ESALs, and subgrade stiffness. We measure the stiffness of the underlying soil layer using the modulus of subgrade reaction, which is denoted as the K value. Concrete slabs also expand and contract constantly with temperature changes, creating severe thermal warping stresses that must be controlled through proper joint spacing. To control cracking and manage joint movement in rigid pavements, engineers use two different types of steel bars. Dowel bars are smooth, thick steel rods placed across transverse contraction joints to transfer heavy wheel loads from one slab to the next while allowing horizontal movement. Tie bars are deformed steel rebar placed across longitudinal joints to physically tie adjacent lanes together and prevent them from separating. Over time, both flexible and rigid pavements develop structural wear and damage, which we call pavement distresses. On flexible asphalt roads, fatigue cracking, also known as alligator cracking, looks like chicken wire and is caused by repeated heavy load stresses. Another common flexible distress is rutting, which creates permanent depressions in the wheel paths caused by uncompacted asphalt or weak subgrade layers. On rigid concrete roads, common pavement distresses include faulting, spalling, and pumping. Faulting occurs when one concrete slab settles lower than the adjacent slab across a joint due to poor load transfer. Pumping happens when heavy traffic forces water and fine subgrade mud out through slab joints, eroding the foundation beneath the concrete. Spalling refers to the chipping or flaking of concrete along high-stress joint edges. One of the absolute biggest enemies of both flexible and rigid pavements is trapped water. Water trapped inside pavement layers weakens the subgrade, causes stripping in asphalt, and accelerates pumping in concrete. Therefore, engineers must design effective subsurface drainage systems, including permeable drainage layers and perforated edge drains, to pull water away from the pavement structure as quickly as possible. Beyond the flat roadway, geotechnical engineering covers the slope stability of roadside embankments and deep earth cuts. When building a road on a steep hillside or constructing a high soil embankment, engineers must calculate the factor of safety against slope failure. If the driving shear forces of gravity exceed the shear strength of the soil, a dangerous landslide will occur along a curved failure surface. When space is limited and we cannot build a gentle, stable soil slope, we must construct a retaining wall to hold back the earth. Common retaining wall types used in transportation projects include gravity walls, cantilever-reinforced concrete walls, and mechanically stabilized earth walls. Mechanically stabilized earth walls, commonly called MSE walls, use metallic or synthetic soil reinforcement straps behind modular concrete panels to create an incredibly strong and cost-effective retaining structure. Finally, when building bridge abutments and major highway structures on extremely weak soils, deep foundations are required. Deep foundations bypass soft upper soil layers to transfer heavy structural loads down to deep bedrock or hard clay layers. Engineers typically choose between driven steel or concrete piles, which are hammered into the ground, and drilled shafts, which are constructed by drilling large deep holes and filling them with reinforced concrete. Congratulations on successfully completing the 5th section of this course. You now have a fantastic understanding of soil properties, pavement structures, distress mechanics, and geotechnical design for transportation projects. I highly encourage you to complete the attached practice test right now, because answering practice questions is the absolute best way to improve your attention and get truly ready for the exam. The practice test is included right here with this lesson to help you actively reinforce everything we just discussed. Keep up this great active learning, and I will see you in the sixth and final section where we will explore construction operations and project management. Welcome to the sixth and final section of our P Civil Transportation course. In this lesson, we are going to explore construction operations and project management, where engineering designs are transformed into physical real-world infrastructure. You will learn about earthwork calculations, project scheduling methods, cost estimation, quality control, and site safety management. Understanding these construction principles is essential because successful engineers must know how to deliver projects on time, within budget, and in complete compliance with safety standards. Get ready for a powerful finish, because mastering these final concepts will tie everything together and complete your exam preparation journey. Let us start by looking at earthwork calculations, which involve moving dirt and rock to bring the ground to the proper design elevation. Before cut or fill operations begin, engineers must account for how soil volume physically changes when it is excavated, moved, and compacted. Raw ground in its natural unexcavated state is measured in bank cubic yards. When soil is excavated, it loosens up and expands in volume, which is known as swell and is measured in loose cubic yards. After soil is transported to its final destination and packed down with heavy rollers, its volume shrinks smaller than its original natural bank state. This volume reduction is called shrinkage, and it occurs because compaction removes air voids between the soil particles. To accurately estimate the number of dump trucks needed to haul soil, engineers use specific conversion factors between bank, loose, and compacted cubic yards. Mixing up these volume states is a very common trap on the professional engineering exam. To plan and optimize massive earthwork operations across miles of highway construction, engineers rely on a powerful graphical tool called a mass haul diagram. A mass haul diagram plots the cumulative volume of earthwork cut and fill along the continuous distance of the project alignment. A rising line on the curve represents a cut area where soil is being excavated, while a falling line represents a fill area where soil is needed. On a mass haul diagram, drawing a horizontal reference line called a balance line identifies equal points of cut and fill. Where the balance line intersects the curve, the total excavated soil volume perfectly matches the required fill volume within that segment. The distance between balance points determines the haul distance, allowing contractors to figure out if it is cheaper to haul soil along the project or simply truck in fill material from an off-site borrow pit. The mass haul diagram also distinguishes between freehile and overhaul distances. Freehile is the maximum specified distance over which soil can be transported without any additional payment to the contractor beyond the base excavation rate. If soil must be moved further than this agreed freehile limit, the contractor receives extra compensation called overhaul. Overhaul is calculated in units of station yards, which represents 1 cubic yard of soil moved across 1 extra station distance. Selecting the right heavy equipment for earthwork operations is critical for staying on schedule and controlling project costs. For short-distance earth moving up to several hundred feet, bulldozers are the most efficient choice for pushing soil directly. For medium-haul distances under a mile, self-loading motor scrapers can excavate, haul, and spread soil rapidly. For long-haul distances, excavators loading large highway dump trucks provide the most cost-effective solution. Now let us transition to construction project scheduling, which keeps complex infrastructure projects moving forward in a structured manner. The primary technique tested on the exam is the critical path method, commonly known as CPM scheduling. A CPM schedule breaks down a complex construction project into individual discrete activities, establishes logical dependencies between them, and assigns specific estimated durations to every single task. In a CPM network diagram, activities are linked sequentially using mathematical relationships like finish to start, or finish to finish. Performing a forward pass calculation through the schedule network determines the early start and early finish dates for every activity. This process establishes the absolute earliest possible date that the entire construction project can realistically be completed. After completing the forward pass, Engineers perform a backward pass calculation starting from the final project completion date. The backward pass determines the late start and late finish dates for every task without delaying the final completion date. Subtracting the early start from the late start gives us total float, which represents the amount of time an activity can be delayed without extending the overall project completion timeline. The critical path itself is defined as the continuous sequence of connected activities that has zero total float. Any delay to a single task located on the critical path will immediately delay the overall completion date of the entire construction project. Identifying the critical path allows project managers to focus their attention and resources on the specific activities that govern the overall project schedule. Beyond scheduling, accurate cost estimating is essential for bidding, budgeting, and financial management during construction. Project estimates are typically created at different stages, moving from preliminary order of magnitude estimates to detailed engineer's estimates based on complete design plans. Detailed estimates multiply calculated material quantities taken directly from CAD drawings by realistic historical unit prices for materials, labor, and equipment. Construction contracts generally use unit price, lump sum, or cost-plus financial structures. Highway and heavy civil projects predominantly use unit price contracts because earthwork and pavement quantities cannot be predicted with total certainty before excavation begins. In a unit price contract, contractors submit bid prices per unit of work, such as per ton of asphalt or per linear foot of pipe, and final payment is based on verified field measurements. Maintaining strict quality control and quality assurance on the job site guarantees that materials meet specified design standards. Quality control represents the operational techniques and field testing performed by the contractor to monitor construction processes. Quality assurance consists of the oversight, independent audit testing, and inspection procedures performed by the owner or agency to confirm that the finished work meets contract requirements. During field operations, concrete and asphalt materials undergo rigorous sampling and physical testing before and during placement. Fresh concrete is routinely tested for slump to verify workability, air content to ensure freeze-thaw resistance, and compressive strength using cylindrical test specimens broken at 7 and 28 days. Asphalt pavements are tested using nuclear density gauges and pavement core samples to verify that required compaction densities are achieved. Protecting construction workers and the traveling public in active work zones requires clear temporary traffic control planning. A standard temporary traffic control zone is divided into 4 distinct functional areas, which are the advance warning area, the transition area, the activity area, and the termination area. Each area serves a specific purpose in safely guiding drivers out of the normal travel path and around the construction site. The advance warning area informs drivers of the construction zone ahead using warning signs and flashing arrow boards. The transition area uses channelizing devices like cones, drums, or barricades to form a gradual taper that redirects traffic out of the closed lane. The activity area contains the actual workspace, material storage, and buffer spaces, while the termination area allows traffic to safely return to the normal roadway pattern. Job site safety is strictly regulated by the Occupational Safety and Health Administration, commonly known as OSHA. Trenching and excavation work presents severe hazards, so OSHA requires protective systems for any trench 5 feet deep or greater, unless the excavation is entirely in solid rock. Protective systems include sloping the trench walls back, benching step levels, or installing mechanical shoring and trench shields to prevent catastrophic soil cave-ins. Contractors must also strictly comply with environmental regulations during active construction operations. Stormwater pollution prevention plans, or SWPPPs, are mandatory documents that outline strategies for controlling erosion and sediment runoff. Installing silt fences, straw wattles, sediment basins, and construction entrance wash pads prevents dirty sediment-laden water from washing off the job site into local waterways during heavy rainstorms. Major congratulations on completing the final section of this course and finishing the entire P-Civil Transportation Preparation curriculum. You have now mastered every core subject on the exam blueprint, from initial project planning and traffic analysis to geometric design, safety, pavements, and construction management. I strongly encourage you to complete the attached final practice test right now, as working through practice problems is the absolute most effective way to lock in this knowledge and maximize your exam readiness. This practice test is included right here with this final lesson to solidify your confidence and problem-solving speed. Thank you for your hard work and dedication throughout this course, and I wish you absolute success on your journey to becoming a licensed professional engineer.